So this is the first lecture in the subject of digital communications. And what we are going to do is to give you an introduction of sorts to this subject in this particular session. So let us start. And we start by asking the question as to what is a communication system? What is it? What is the entity which is called as a communication system? So it is an entity which transmits information from source to destination. That is the simple definition of a communication system. Now the next question that we ask is what kind of information? All kinds of information. It can send text, it can send image, it can send audio and video. So let me repeat that. The kind of information that a communication system sends can be any of these four or all the four. For example, the small equipment which we call as our mobile set is capable of handling all these four aspects of communication systems. Now, mobile communication system is not the only system in the world. There are many communication systems. And what we are going to do in this particular introduction is to tell you how to compare various communication systems. What are the parameters based on which various communication systems can be compared? All right. Now there are many parameters. We are going to concentrate on a few. And what are these? The first one is the distance. Some of the communication systems send signal over vast distances, whereas some of them are required to send signal only over a short distance. So distance is one parameter by the help of which you can compare two communication systems. Another is number of users. Some of the communication systems have large number of users. Some of them will have small number of users. So this is another aspect based on which you can compare communication systems. The third one is the rate at which the data is sent in bits per second. So some of them will be quite fast, some of them would be slow depending on the application. And finally, information rate, the rate at which the information is sent. Note that the data rate is not in general same as the information rate, and we'll point out the difference in this introduction. Alright, so as we said, these are some of the aspects which will enable you to compare different communication systems. Let us look at some examples of communication system where distances are different. For example, if you consider a satellite communication, it is capable of sending signal over a vast distance. On the other hand, if you consider the signal which is transmitted from base station to mobile, then the distance is quite small. Okay, this may be of the order of a kilometer or a few kilometers at the most. Okay, so this gives you a couple of examples where the distances which the communication systems use are different. Okay. Then let us look at the second aspect, that is number of users. Now if you consider FM broadcast system, there are a number of FM transmitters working in the same city. So all of them radiate energy into same space. Okay, so a number of radio stations send the signal into the same space. So number of users from transmitting viewpoint are also large, and in fact the number of receivers are enormously large for the FM systems. So as we said, many stations transmit signals into same space. Also very large number of receivers, large number of users. But incidentally note that this is a one-way communication, in the sense that the FM transmitter sends the signal to the FM receiver which the user uses, but the user himself does not transmit any signal information back to the transmitter. So in that sense, this is a one-way transmission. Anyway, so this is one example of number of users where large number of users are present. Let us now consider one more example where you have large number of users, and this is well known. Okay, I have already said that this is one-way communication. Let us now look at the mobile system, and all of us know that mobile system certainly uses very large number of users. But note that here the communication occurs which is bidirectional. That is, two subscribers can talk to one another. So one can send a signal to the other and the other can also send a signal back. And even if you consider the intermediate system, that is base station and the mobile receiver, then it is again a two-way communication. That mobile sends information to the base station and the base station also sends information to the mobile. So this is another system where we find that the number of users is quite large. And incidentally, this particular system is bidirectional. Okay, let us now look at a system where the number of users are not going to be large. For example, consider ship-to-shore communication system. So when you have a ship-to-shore communication systems, the number of users which are required to operate these systems are quite small. They do not have very large number of users. All right. So we have considered two aspects so far. One is the distance by which you can compare the communication systems, and there is the number of users by which you can compare the communication systems. Now the third aspect that before considering the third aspect, let us see what are the resources which will allow the communication system to transmit signal over long distance. What are the resources? And also, what is the resource which will allow the communication system to address a large number of users? So what are the resources required to satisfy the requirements of the two aspects? Distance may be long, number of users may be long. Now there are a number of resources, but we'll focus on the two important ones. The first one is the transmitted power. Larger the power that is transmitted, the distance over which the communication is possible also will be larger. Why this is so? Because whenever you transmit a signal, whether it is a line communication system or it's a wireless communication system, there will always be attenuation over this transmission. When the signal is transmitted, there is attenuation. So you may transmit large power at the transmitter end, but by the time it reaches the receiver, the signal may be quite small. And if it is not able to overcome the noise which is always present, then the communication will not be feasible. So one simple way you can think of to be able to increase the distance of communication is to increase the transmitted power. So that's why we say that transmitted power is one resource for fulfilling the distance requirement. All right. What about the number of users? How do you satisfy the requirement of large number of users? Now again, there are many ways in which this is achieved, but we'll look at one important aspect, and that is, so this we have already discussed. Let us now talk about the resource for the number of users. So that is the bandwidth. Larger the bandwidth, larger is the possibility of having large number of users. So let's give an example of this, but before that let me just repeat. Larger the bandwidth, larger is the number of users. In order to understand this, let us take an example. Again, take the example of FM broadcast and let us try to see the number of FM stations that can operate. So the total bandwidth that is allocated for FM broadcast is from 88 to 108 megahertz. So that is a total of 20 megahertz. Now, for the FM signal to be transmitted, each station requires a bandwidth of about 200 kilohertz. How this comes about, etc., is a details of the communication system, and which we are not addressing right now in this introduction part. But just note that every transmitter requires a bandwidth of something like 200 kilohertz, and this includes the guard band. Understand that each station actually may require a bandwidth which is about 180 kilohertz. But then, since filters are not perfect, when the receiver has to distinguish between two stations, some guard band is required. So including the guard band, you can say that each station occupies 200 kilohertz. So the total number of stations that can operate, that can inject the signal into same space, mind you, space is the channel which is carrying the signal, and number of stations are putting signal into this space. But how many? Okay, so 20 megahertz is the total bandwidth. 0.2 megahertz, that is 200 kilohertz for each station. So the total number of stations that can operate is as much as 100. So this tells you why having a large bandwidth available for a particular communication system will allow you to use a large number of users of the common channel. Okay. The next aspect that we want to consider, again, let me revise. We had said distance is one aspect, then number of users is another aspect, and we have seen the resources which are used for fulfilling the requirements of these two aspects. The third aspect by which the communication systems can be compared is the data rate. So this is one more parameter with which the communication systems can be compared. So in order to understand the calculation of this data rate, let us look at some of the basic concepts by which the digital communication system operates. So how the information is transmitted in a digital communication system? Basically, it is a sequence of messages. You transmit first message, then second message, and this will be from a set of messages. So the set of messages could be of varying size. There may be only 2 messages, there could be 4, there could be 8, and so on. But whatever message that you transmit will be one out of these set of messages. Now the question is, what is a message? The answer is, it depends on the system. For example, if you are trying to transmit an analog signal via digital communication system, you must first convert it into a digital signal. So you have to do the sampling operation. So the sample of an analog signal can be considered as a message. Or maybe the signal is already available in the discrete form, but you code it in a certain way, maybe 8-bit ASCII code. So that is also a message. So you can think of number of possible messages. So what we are saying is that in a digital communication system, information is transmitted as a sequence of messages. And what are we answering next? We are answering what is a message. So it depends on the application. It could be the sample of an analog signal which has been obtained and converted into a certain number of binary digits, maybe 8, 16, and so on. So each group of these binary digits will be a message. Or it could be a ASCII code, or it could be some other code. Alright. So what we have said is how the digital communication system sends the information. It sends as a sequence of messages, and we have said what is a message. Alright. Now, how do you calculate the bit rate? So, bit rate is in bits per second, and it depends on sampling frequency or the message rate and the number of bits in each sample or in each message. So, as an example, consider the speech signal. The sampling rate is 8,000 samples per second and number of bits in each sample is 8. In that case, the bit rate is 8,000 multiplied by 8, 64,000 bits per second. So this is the famous 64 kilobits per second speech rate which has been historically used. These days you can use much smaller data rate for representing speech by using codecs, etc. But this is the one which has been historically used. And this is how you calculate the data rate. Okay. So what did we say? We said that digital communication system transmits information by sending a sequence of messages. Each message can be a coded sample, or it could be a coded discrete source itself. And then to calculate the bit rate, you need to know at what rate messages are sent or at what rate samples are sent. So you need to know what is the sampling rate, and then you need to know what are the number of bits in each sample. So once you know that, by simply taking the product, you can calculate the bit rate. Alright. So this is the third aspect by which the communication systems can be compared. Some of them may have fast bit rate, some of them will have low bit rate. Now, one more important aspect that we need to consider is the information rate. Understand that bit rate is in general not same as the information rate. So we will try to explain it here. All right. So this is the rate at which the information is sent. So since this is the information rate, you need to understand what is an information content of a message. When you send a coded message, maybe 8-bit, 16-bit, or whatever it is, how much information it contains. All right. Now information we understand qualitatively, but now what we want to do is to convert our qualitative understanding into a quantitative one. We want to define a measure for information. So what we'll do is we'll first try to discuss how we understand information qualitatively, and then out of that how can we have a reasonable mathematical definition for the information. Okay. So information content of a sample or a message. So let me show you a couple of example messages. Suppose someone says that the sun rose in the east today, or someone says that sun will rise tomorrow. Now these kind of statements hardly give you any information, because you are reasonably certain that the sun is going to rise next day. Even if someone tells it to you, it doesn't tell you anything special. So the probability of the event occurrence of this event is so high that it doesn't give you any information at all. But if you consider a statement which says that a new element has been discovered, then this is something which is not an everyday occurrence. The probability of the occurrence of this event or this message is quite small, and it conveys more information. All right. So this is our qualitative understanding of the information. We now want to convert it into quantitative one. So clearly, smaller the probability, larger is the information. But we can't simply use 1 by p as the mathematical definition, because if p is equal to 1, then it will mean that information is also equal to 1, which is not so. If the probability of the occurrence is very high, then the information content is going to be low. So we need a mathematical definition which is consistent with our qualitative reasoning. So one possible definition is I log of 1 by p to the base 2. To the base 2, because most of our systems are binary and it is convenient to choose this particular base, although it is not mandatory. So in this case, what will happen? If p is equal to 1, then log of 1 to the base 2 is going to be 0, and that is what we want. If an event is certain to occur, it doesn't give you any information at all. But as p reduces, the information content increases. So since this is in the denominator, clearly this will increase. Now, in any communication system, you have a set of messages, and each one of these messages from this set do not have same probabilities. Okay, so for example, you send a message which we call as M1, it may have a probability P1, and for this probability P1, the message will have a certain information which can be calculated by using this formula. Then if you consider the second message, its probability of occurrence in general will be different, and the information therefore carried by it will be different. In that case, how do you summarize this information content? So what you do is you calculate the average information per message, and there are ways of doing it which later on we'll study. But for the speech signal, some empirical techniques, it can be found average information per sample. So if the speech is coded into 8 bits, the average information in this sample of 8 bits is only 2 bits. So clearly the information rate now we said that the speech was sampled at 8,000 samples per second, and when we the bit rate was 8,000 into 8, that was 64k. But this 8-bit message contains only 2 bits of information. So the information rate is not same as the bit rate. So information rate then will be 8,000 samples per second multiplied by 2 bits per sample. So this is 16,000 bits per second. So note that this particular method of sending information is not very efficient, because you are using a bit rate of 64,000 bits per second. That is the physical data rate, whereas the information that is sent is only 16,000 bits per second. So there are ways of improving this, and later on we will be studying this. Alright, so that is as far as the information rate is concerned. Now, what are the parameters which can control the information rate? So there are a number of them. So as we said, R is the information rate in bits per second, and the important parameters by which this rate can be controlled. See, we would like to increase this information rate as much as possible. So what are the resources available? So the resources available, one is transmitted power. Then depending on the method of coding and decoding, you can control the information rate. Depending on the method of modulation and demodulation, you can control the information rate. Depending on how you use antenna arrays, you can control the information rate, and so on. So as you can imagine, the designer generally would like to improve the information rate as much as possible, so you get good efficiency for the given physical data rate. Okay, but what is the highest information rate that he can achieve? Now there is an upper limit for that, and that is obtained by a law called as a Shannon-Hartley law for channel capacity. And this gives the upper limit for the rate at which the information is sent. So whenever anyone designs a communication system, and if he wants to know how good his communication system is working, all he has to do is to compare his own information rate that is achieved in his system with the rate that is given by the Shannon-Hartley channel capacity. So what is the equation for this? B log 1 plus S by N. And what are these various variables? What do they mean? B is the bandwidth. S by N is the signal to noise ratio at the receiver. So you can imagine that the information rate can be controlled by two factors. One is the bandwidth. If you increase the bandwidth, then the channel capacity increases. Similarly, if you increase the transmitted power, then the received signal power, mind you, this is the received signal power to noise ratio. So if you increase the transmitted power, then S by N will increase and the channel capacity will increase. So the point is, you have got a certain channel. It has a certain bandwidth and a certain power you are transmitted at the transmitting end. So this will decide what is B and what is S by N. It will decide that. Now you can either increase B in order to increase the channel capacity, or you can increase the transmitted power in order to increase S by N ratio. Okay, so this gives you some kind of a trade-off. You can either increase large amount of bandwidth, or you can increase the signal to noise ratio by increasing the transmitted power. So as we said, B is the bandwidth, S by N signal to noise ratio, C is the information bits per second. Mind you, this is not something which is actually obtained. This is the upper limit that can be obtained by communication systems, and very few communication systems will approach this. Many communication systems will operate only at 50% of the channel capacity. Some of them can operate at 80%, some of them can operate at 90%, and so on. But they can never overcome this particular limit. So R is the actual rate of information for a given system, and it is always going to be less than the channel capacity. Alright, so in this introduction, what we have seen is number of parameters by which the communication systems can be compared with each other, and what are the resources by which these parameters can be controlled. So there are control parameters and controlling parameters. So the parameters by which the communication systems are compared, we discussed distance, we discussed number of users, we discussed physical data rate and the information rate. And we also said that the number of resources which are available are the power transmitted, the bandwidth, the nature of modulation, demodulation, the nature of coding and decoding, and so on. And we have also seen the upper limit for the information rate that can be transmitted over a given channel. So given channel means what? The bandwidth of the channel is known and the transmitted power at the transmitter end is known. For this, you have got an upper limit for the information rate. And that's all as far as this session is concerned.